Integral as a net change. Net change. We want to use integrals and the area interpretation of a definite integral as a way of computing net change or total change in something, in some quantity. So here we have the net change as the integral of a rate. Well, we're going to start by saying that the net change in Q of t, where Q of t represents a quantity of something, over an interval t0 to t1, some time interval, is given by the following integral. So the net change in quantity over t0 to t1 is the integral from t0 to t1 of q prime of t dt, which of course by the fundamental theorem of calculus is equal to q of t sub 1 minus q of t sub 0. So essentially here, q represents an amount of something. If we take the derivative of q, q prime of t, that's a rate of change of quantity. So if I integrate a rate over some time interval, what will come out is the net change in quantity. So this is really just, again, the fundamental theorem of calculus, but with some application. We are used to the fundamental theorem of calculus as the integral from a to b of f prime of x dx is equal to the antiderivative of f prime, which is f, evaluated at b, f of b, minus f of a. So here now we're instead just using q as the quantity function, and so when we integrate a rate, I get a net change in quantity. And we can also rewrite this equation. We can solve it for q of t1. So if I add q of t0 to the other side, to the integral, then we have this equation which says q of t1, the quantity of something at time 1, is equal to q of t sub 0, which is the initial quantity, plus the integral from t0 to t1 of q prime of t dt, the net change in quantity. So it should intuitively make sense that the quantity at some time 1 is equal to however much you started with, the initial quantity, plus the change in quantity over a time interval. Did you add to the initial quantity, or did you take away from the initial quantity? Now, quick note, a rate will not always be given using prime notation. So we are going to be integrating rates of change, but we may not see the prime notation. We would know we have a rate based on the units. So very informally here, we're saying that the integral from t sub 0 to t sub 1 of a rate of change of something is equal to the net change in somethings between time 0 and time 1. Let's look at an example. The power used by an appliance is given by P of t is equal to 2 plus sine of the quantity pi t divided by 12 joules per hour. How much energy is consumed during a one-day period, which is t from 0 to 24 hours? Show all work that leads to your answer, include units. So here we are given a rate function. Even though the notation isn't prime, we can see in the units, joules per hour, that we're given a rate. And what we want is a net change in energy. How much energy was consumed over the time interval from 0 to 24. So we're going to go ahead and set up an integral. Our integral is going to extend from 0 to 24. So I'm going to say t equals 0 to t equals 24 hours. And we're going to integrate the rate, 2 plus sine of pi t over 12. So we have 2 plus sine. I'm going to express this as sine of pi over 12 times t dt. All right, so now it's a matter of performing this integration. The antiderivative of 2 is 2t. And then we're going to have the antiderivative of sine of pi over 12 times t. Well, the antiderivative of sine is negative cosine. So we'll have negative cosine of pi over 12 times t. But it's not just t, it's pi over 12t. So what has to go in the front of cosine is the reciprocal. So that would be 12 over pi. So there's my antiderivative of the integrand, and it's a definite integral. So we're going to have to substitute in 0 and 24. So first we're going to substitute in 24 and then 0. So we're going to have 2 times 24 minus 12 over pi cosine of 2 pi. So here 24 divided by 12 is 2. So cosine of 2 pi. So that's plugging 24 into each t minus, now we'll plug 0 into each t. So minus 2 times 0 minus 12 over pi cosine of 0. So I'm keeping that second piece in parentheses because the negative would distribute there. Well, 2 times 0 is just 0, and so that's gone. But cosine of 0 is 1. So I have just minus 12 over pi from the second piece over here. So let's go ahead and put 48 minus, so we have cosine of 2 pi is the same as cosine of 0. So that's also just 1. So I have minus 12 over pi, and then we said plus 12 over pi because this negative distributes. So those actually cancel out and give us 0. So we end up with just 48. All right, well, 48 what? We were supposed to include units in our answer. So what would the units be? Well, here is a graphical representation of the function p of t. And so we just did a definite integral. So we found the area between the function p of t and the t-axis between 0 and 24. So we just found this area here. But let's try to think about what the units of that area would be, because we know the numerical value is 48. But when we're calculating area, you know, we started by using rectangles originally to approximate area. And so with rectangles, we think base times height. Well, the units of the base is in hours, and the units of the height is in joules per hour. So if we multiply hours times joules per hour, the units that cancel are hours. So we're left with joules, which is a measure of energy, and that's what we're being asked for, how much energy is consumed. So 48 joules is our final answer. In this example, we're told that there is initially 10 feet cubed of water in a tank. Water begins flowing into the tank at a rate of r of t equals t squared feet cubed per minute. Part A is asking how much water was added to the tank during the first 3 minutes. Show all work that leads to your answer and include units. So this question is asking us about the net change. How much water was added to the tank during the first 3 minutes? So the time interval here is from 0 to 3 minutes. We're going to set up our net change integral as the integral from time 0 to time 3 of our rate function. So we can see it says rate, but we can also see the units are a rate, feet cubed per minute. So we're going to be integrating just t squared dt. And so the antiderivative of t squared is nice. It's t cubed over 3, or 1/3 t cubed, evaluated from 0 to 3. If I substitute in 3 first and then 0, I end up with 3 cubed is 27. 27 divided by 3 is 9, and then minus 0. So I end up with just 9 as my numerical answer. But now let's think about what the units would be. So when we integrate a rate over this time interval in minutes, what's going to happen is that the rate here is going to cancel out. The minutes are going to cancel out, and I'm just going to be left with feet cubed. And that should make sense based on what the problem is saying, because we want to know how much water was added to the tank. So water is a three-dimensional quantity that should be represented by three-dimensional units like feet cubed. So we have 9 feet cubed as our answer to how much water was added to the tank during the first 3 minutes. This is the net change during the first 3 minutes. There is a part B which asks a slightly different question. How much water is in the tank after 3 minutes has passed? Again, show all work that leads to your answer and include units. The previous question asked us how much water was added to the tank during the first 3 minutes. But now we want to know how much water was in the tank after 3 minutes had passed. That means we need to take into account how much was in there initially. So in other words, the answer to part B is going to include that initial 10 feet cubed of water. So this is our initial amount. And then we need to add to it the net change, which we calculated in part A. So the net change is that integral from 0 to 3 of t squared dt. So we have the net change on the interval from 0 to 3, which we calculated as 9 feet cubed of water. So we have the initial amount, 10 feet cubed, plus the net change. So it was a positive change. We were adding water to the tank. And so after the 3 minutes has passed, we have a total of 19 feet cubed of water. In this example, we have the acceleration of a particle is given by the equation a of t is equal to t cubed plus 2t plus 4 feet per second squared. Find the net change in velocity between t equals 0 seconds and t equals 2 seconds. Include units. So here we're being asked for the net change in velocity, and we were given acceleration. So when we integrate acceleration, we are going to get velocity. And so when we integrate from 0 to 2, we're going to get that net change in velocity over that time interval from 0 to 2 seconds. So once again, we'll set up our integral. We're integrating from t equals 0 to t equals 2 of t cubed plus 2t plus 4. Here we have t to the 4th over 4 plus 2t squared over 2. The 2's will cancel, so t squared plus 4t evaluated from 0 to 2. And so if I plug in 2 here, 2 to the 4th is 16 over 4 is 4, plus 2 squared is 4, plus 4 times 2 is 8. And then when I plug 0 into those three terms, I'm just going to get out 0. So we end up with 16. But now, let's go ahead and talk about what the units would be. Well, we can see that we're trying to find net change in velocity. So the units of velocity would have to be in feet per second. So we have feet per second. Now, if we bring in that graphical interpretation, even though we don't have the exact graph, the graph might look something like this. We are integrating from 0 to 2, and on the horizontal axis, we have units that are in seconds that represent t. And then on the vertical axis, our acceleration is in feet per second squared. So here, that area we found was 16. And then when we multiply the units, feet per second squared times seconds, so feet per second squared times seconds, one of the seconds in the denominator cancels. So we have just feet per second left over. So units are always a great check in just making sure that we've done the correct operation. So integration was the right way to go to get from feet per second squared to feet per second to get from acceleration to velocity. Now we're going to talk about a special kind of net change. When the rate that we're discussing is velocity, we have special names for what comes out as the net change. We call it displacement and total distance traveled, depending on which function we're integrating. So if an object travels in a straight line with velocity v of t, then displacement during this interval from t0 to t1 is the integral from t0 to t1 of just the velocity function dt, the integral of v of t dt. And this should make sense because v of t is the derivative of position, s prime of t, and so when we integrate s prime, we get s, the position function, so we have the change in position, which is displacement. So it's just a special name. We're still talking about net change. The net change in position is called displacement. But total distance traveled is slightly different. If we want to calculate total distance traveled over the time interval from t sub 0 to t sub 1, we're going to perform an integral from t0 to t1, but this time, instead of integrating v of t, we have to integrate the absolute value of v of t dt. So that's because distance is always greater than or equal to displacement, right? It's taking into account all of those different pieces of where I start and where I stop and adding those pieces together to get that total distance traveled. Let's go ahead and do an example. We're given the velocity of a particle is v of t equals t squared minus 4 in feet per second. The graph of v of t is given. Find the, part A is asking for the displacement over 0 to 5 seconds. So it's a matter of remembering that displacement is having us use just the velocity function. So our integral is going to be the integral from that time 0 to time 5 of just v of t dt. So that's 0 to 5 of t squared minus 4 dt. So we're going to go ahead and find the antiderivative, t cubed over 3 minus 4t, evaluated from 0 to 5. If we'll plug in 5 cubed is 125 over 3 minus 4 times 5 is 20. If I plug in 0 into each of those t's, I'm just going to get a 0 in each case. So now I have 125 over 3 minus 60 over 3, those common denominators. So I get 65 over 3 as the displacement. And the units there are going to be in feet. So this is my exact answer. It's approximately 21.6 feet as my displacement, or again, it's still a net change of position. Now let's go ahead and graphically shade the region that this represents. So this is my velocity graph over here. This is v of t, and we did the integral from 0 to 5. So we went ahead and found that the area from, in this case, 0 to 2, which is below the x-axis, plus the area from 2 to 5, which is above the x-axis, that when you add these two together, you get out that 65 over 3. So this part below the x-axis would be negative, this part above the x-axis would be positive. When you add those together, that net or total change is going to be about 21.6 feet. Now for part B, we want to calculate the distance traveled over 0 to 5 seconds with that same velocity function. our integral setup goes from 0 to 5 of the absolute value of v of t dt. So we have the integral from 0 to 5 of the absolute value of t squared minus 4 dt. Now, unfortunately, what we cannot do is ignore the absolute value bars. Or sometimes what students want to do is just kind of pull them to the outside and they calculate the integral ignoring them and then just kind of make the final answer positive. We can't do that. It doesn't work. Let's take a look at graphically what we need to do so that we can understand why that doesn't work and then the setup for what we actually do need to do. So back over here, I'm going to go ahead and put those shaded regions from before back up. So when we did displacement, we had the area that was below the x-axis, which was negative, plus the area that was above the x-axis, which is positive, and we added them together. When we're working with the absolute value of v of t, what that does is it takes any part of the function that's below the x-axis and makes it positive. So it essentially reflects that part that's below the x-axis up and makes it positive, which makes that area positive area. So what we need to do is we need to find the area that's below the x-axis and make that positive, and then we need to add it to the area that's above the x-axis. So I am going to need to split this up into two separate integrals. Now, because I have the graph, I can see that I'm going to have to split it up at the t value 2. If I didn't have the graph, I would have to do the calculations to find when is the object at rest. When does v of t equal 0? So I'd have to solve this equation. When does v of t equal 0? When does t squared minus 4 equal 0? Well, if I factor that, I get t minus 2, t plus 2. So I get positive 2 and negative 2. Well, I'm only concerned with positive values for time, and so that's why I'm just going to use 2. So if I didn't have the graph, I would have to do this additional step for finding where is the object at rest to know where I break up my integrals, because I'm going to need two integrals. So this one integral here is going to split. We're going to go from 0 to 2 of t squared minus 4 dt. Well, looking at the graph, I know that the regular v of t graph is below the x-axis. So this integral right here is going to give me a negative number. It's going to give me this shaded region that's below the x-axis. But I want it to give me this flipped region that's above the x-axis. So what I'm going to do is do this computation and then make that quantity positive. So I am going to put absolute value bars around the whole outside of it. And that's going to give me that 0 to 2 part. And now I want the rest, the integral from 2 to 5. So the integral from 2 to 5 of t squared minus 4 dt. Now, technically, because we have the graph, we know that the integral from 2 to 5 is going to be a positive quantity. But again, let's pretend that we don't have the graph because it will not always be provided. If it doesn't have the graph, then we couldn't assume that this is a positive region. So just to be safe, we'd put absolute value bars around the outside of that quantity. So then we would go ahead and evaluate each of these two integrals inside here, which no longer have that issue of an integrand with absolute value bars. We were able to go ahead and move them to the outside because we broke it up into the two integrals we need. So here, this would be t cubed over 3 minus 4t evaluated from 0 to 2. All that's in absolute value bars. The same over here, t cubed over 3 minus 4t evaluated from 2 to 5. So I'm going to go ahead and skip sort of the computational part here. We're plugging in 2 and plugging in 0, and I'm just going to give you that value. This is going to be negative 16 over 3. Again, we knew it was negative because it was originally below the x-axis. And this part here, if you plug in 5 into both t's and 2 into both t's and subtract, we get a positive quantity. We get 81 over 3. So it's like basically this part down here was negative 16 over 3. This is 81 over 3, but we flipped it and we made it positive, so this is 16 over 3, and then we're going to add those two pieces together. So when we do that, when we add positive 16 to 81, we get 97 over 3. So we have a total distance traveled of 97 over 3 feet, which is about 32.3 feet. In this example, we're told the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. A table of selected values of r of t in the first 90 minutes are shown numerically and graphically. This is kind of interesting because we're used to being given an equation for a rate, but this time we are given just a few rates at different times in a table and then graphed. So we have at 0 minutes, the plane is consuming 20 gallons of gas per minute, and 30 minutes later, 30 gallons per minute, and then at 40 minutes, 45 gallons per minute. So there's these different times where this information is being recorded during an airplane flight, how much gas is being used in gallons per minute right at these particular times. So we have numerically the data shown, and then graphically the data shown. And we're told that this function, r of t, is a twice differentiable function. That just means that we can take its derivative twice. So this is not a second derivative. It means that we can take the derivative twice. And we're told that r of t is strictly increasing. So because we are given just a few snippets of information, we can't assume that just because those snippets of information look like they're increasing, that the outputs are always increasing. But we know that because we are told that piece of information. So here we know that the actual r of t function will always be increasing over that 0 to 90 minutes. We don't know exactly what the graph looks like, so we can't connect the dots, but we know that this function will just continue from left to right to go up and up and up. So now let's see what the question is asking us in part A. Approximate the integral from 0 to 90 of r of t dt using a left Riemann, which means rectangular, sum with 5 intervals. So we're going to approximate the integral from 0 to 90 of r of t dt. Now we can't find this exactly because we don't have the function. We can only approximate it because of our limited amount of data. So let's go ahead and do that part of the question first. We're going to approximate the integral from 0 to 90 of r of t dt. So this is going to be approximately. All right, so using 5 intervals. Well, the first interval extends from 0 to 30 minutes. So that's the base of my first rectangle. So here from 0 to 30, so my base is 30. And if I'm going to be using a left Riemann sum, then from 0 to 30, the height that I'm going to choose has to be the leftmost height, which corresponds to 0, because 0 is on the left of 30. So the height I'm going to choose is 20. So this is my height number 1. So my first rectangle has a base of 30 and a height of 20. So essentially, graphically, what we're doing is we're creating this first rectangle here. So we are finding this amount of area here. And then we move on. The next rectangle is going to have a base of 10, the difference between 30 and 40. And then the left height is going to occur at 30, and the output there is 30. So this is going to be my next height. So this is going to be my second height. And so my second rectangle will be plus 10 times 30. So graphically, we have just found this second one here has a base of 10 and a height of 30 using that left point. And so on. So we're going to keep going with this. The next one has a base of 10, the difference between 40 and 50, with a height of 45. So this is height number 3. So plus 10 times 45. And so here's that next rectangle. And we have 2 more. So we'll have a base of 20 for the next one between 50 and 70 with a height of 50. That's height 4. So we'll have plus 20 times 50, another base times height. And that's going to be this one here, a base of 20 from 50 to 70 with the height on the left there. And then finally between 70 and 90, that has a width of 20. And the height is going to be 65. So this is going to be our 5th height. So we're going to have plus 20 times 65. And so our last rectangle, whoops, is going to go from 70 to 90. And there we go. So we are not going to use that last output value, right, because we're doing left rectangular sum here. And something else to observe is that the widths were different. So this would not be considered L5. So we don't have a uniform delta x. There is no delta x. This is like a delta x1 and a delta x2. So there's a different width over the various rectangles. So that's why we had to do each one separately. And so if you were to multiply and then add it all together, you're going to get 3,650. And the units there are going to be in gallons. So this table, the horizontal axis is time in minutes. So this is t in minutes. And then this is r of t in gallons per minute. So we are integrating a rate, or approximately integrating a rate. And so the units of minutes are going to cancel out there. So we're just going to have gallons. So here's our approximation. And then is this numerical approximation less than the value of r of t dt? Explain your reasoning. So can we for sure say that this is less than the actual area under the curve, what this integral represents? Well, because we were told that the function is always increasing, we don't know exactly what it looks like, but let me give one possible example. Since we're always increasing, if I connect the dots like this is an always increasing function, I can see that there's a gap between my rectangular approximation and my function. So yes, because I am told that my function is strictly increasing, I do know that this numerical approximation is less than the actual value. So I do need that piece of information and to cite that piece of information to show it. So I'm gonna erase this because we don't know for sure that that's what it looks like, right? So that was just like one possibility. But I just wanted to sketch that out before I write down my reasoning for why, yes, this is true. So I want to say something like, since r of t is increasing and we used left endpoints, this is an underestimate. This is an underestimate for the actual integral from 0 to 90 of r of t dt. It would be an overestimate if I had used right endpoints, because then I'd have these rectangles that always go over the graph of r of t. In part B here, we are asked to explain the meaning of the integral from 0 to 90 of r of t dt in terms of the fuel consumption for the plane. So we spent a whole part approximating this value, but why is this value important? What does it mean? So we have the integral from 0 to 90 of r of t dt. Well, it's the net change. It's the net change in gallons. So we wouldn't really say that though if we're explaining this to somebody, right? So it's the amount of fuel in gallons that the plane consumes or uses during that first 90 minutes of airplane flight. So we integrated a rate to get a quantity, and that quantity is an amount. So this integral is the total amount of fuel, right, in gallons. We always want to include the units in our explanation. In gallons consumed by the plane, and we also want to cite the time. So consumed by the plane, you can say during 0 to 90 minutes or during the first 90 minutes. I'll go with that, during the first 90 minutes. Actually, I don't want to say first because it doesn't really say that. It says during an airplane flight, we just kind of start recording. So it's not necessarily the first. So consumed by the plane during 0 to 90 minutes. The 0 to 90 minutes of the recording time, right? Because it doesn't really say that's the first 90 minutes. It's just all of a sudden we start recording the rate of fuel consumption. So we want to be able to explain the meaning of the integral, really using units to help us understand, and the time interval matters as well. We wouldn't want to just say this is the integral from 0 to 90 of r of t dt. That's just reading it. We also wouldn't want to say this represents the area under the curve r of t dt. That's true, but it doesn't explain it in terms of the fuel consumption of the plane. So we really want to bring in the units, the time interval, you know, what's happening, talk about the plane, to really explain what's going on. Finally, in part C, use data from the table to find an approximation for r prime of 35. Show computations that lead to your answer, include units of measure. So remember, this is r of t graphed over here. So again, the horizontal axis was in minutes and the vertical axis was r of t in gallons per minute. Now what we want to approximate is r prime of 35. That's the derivative of this function. And the derivative is the slope of a tangent line. So let's kind of sketch up a possible graph. Again, we don't know exactly what this looks like, but we know it's always increasing and differentiable, so no crazy sharp turns can happen, right? So I want an approximation for the slope of the tangent line at 35. 35 is right here. So it's like I would want an approximation for the slope of this tangent line. I missed a little bit, right? Something like this. Well, to find an approximation for the slope of a tangent line, we can always use the slope of a secant line. So a secant line is going to pass through 2 points. So we'll pick the 2 points nearest 35, which are 30, 30 and 40, 45. So we're going to focus on these two pieces of information here. And we're going to say that r prime of 35 is approximately r of 40 minus r of 30 over 40 minus 30. So the slope of a tangent line is approximately the slope of a secant line. And we know these values are 45 minus 30 over 10, or 15 over 10, or 1.5. But now let's talk units. We took a derivative of a rate. So here, what might help is if we recognize that r of 40 minus r of 30, those outputs were in gallons per minute. So here, this was in gallons per minute, and 40 minus 30 were in minutes. So we have gallons per minute, which is gallons per minute squared. So the derivative of a rate, right, looks like that acceleration type of unit.